So I'm going to get started. I'm Harold Carr. I work at Oracle Labs as of last October and doing blockchain scalability research. And this talk assumes you know zero about blockchain, so it's very introductory. It's in Haskell, but I've tried to use really simple Haskell so it's easy to understand. And that's the link to all the code for this talk. And I'll come back to this slide later on some other books and papers that I have found useful that you might want to check out too. But let's start right out with what is a blockchain. Everybody's pretty used to logs in their processes. Like, here's a single threaded process and it just writes to the log. And you keep writing the same, different stuff to the log, and it's in order, and you go see to the log sooner or later to see what's going on. That's essentially what a blockchain is just another log. And if you've got a process with multiple threads, then you probably need to put some sort of locking around the log so things come out in the right order and they don't get interleaved I/O type of effects. So there's other things to think about. And of course, those different threads can actually be responding to communication from the outside world. And let's say they're all on an accept at a channel or something, and then there's a different thread running on each client connection, and they're dumping stuff into a log. Same idea. And, oops. Sometimes, for reasons of scalability or other things, you might actually, before you actually put them into the log, you might actually dump them into some sort of pool. And in that case, you don't really care about the order. There's some reason you're putting in this pool, and there's a lock around it. And then we have these one or more threads that are grabbing one or more things out of the pool and deciding which ones will actually go into the log. And that's where the idea of mining comes in, is there's a bunch of things and these people are trying to decide which ones to go into that log. But it's still just on one machine, so it's not distributed. The next idea is the same thing, where you have a bunch of threads. They're all dumping things into a pool. You have some minor thread, we're calling it a minor thread, but just some decider thread that decides, which one or more of these things in the pool are going to go into the log. And furthermore, because there's now two processes on it's the same machine, different nodes across the country, it doesn't matter. When they get this information, they actually share the things that are coming in on the network, from the network, with each other. And when they finally update their log, they even share what their updates with each other. And the trick is, with blockchain, is to keep these two logs in sync. And that's what consensus is all about, is to make sure that eventually they have the exact same copy of the log. So in a little more detail, and this is where we're going to start dropping into, is you have some sort of clients that are, I'm calling them commands, but you could think of them as transactions. And so you're adding some sort of command or transaction to the system, and that system is going to tell everybody else about it, so all their peers, on some sort of peer communication system. And once they have told everybody, they're going to add it to their ledger. Well, I was calling it log before, now I'm calling it ledger, and I also call it chain, which it confuse you, but it's also a good idea because you're going to hear chain, ledger, log as kind of interchangeable when you hear about blockchain. And one thing what I didn't talk about, and I'm not going to talk about until the very end of the talk, is this idea of smart contracts. We're going to leave that out for the time being because it's actually not necessary to understand the fundamental operation of just the chain part of things. So let's start looking at code. And as usual, lots of imports and language pragmas. But starting right out with the block. So when you say blockchain, it just means a chain with blocks in it. And in this blockchain, You've got a previous hash, which we'll talk more about, an index, which is just where it lives in the chain, the transactions, and a proof, which is also called the nonce. And so as we move along, each one of those things will become clear. For now, the transactions are just an uninterpreted byte string. And the only property the transactions in this initial system have is equality. So we're not going to let two transactions that are equal go in at the same time or ever. But that's the only thing. Other than that, they're just uninterpreted byte strings. So that is a block, pretty simple. And the previous hash just means when I put something into the chain, I'm going to have a hash that points to the block that is the hash of the previous block. And that means if anybody changes it, you can detect it very easily. And you'll hear this too. You hear people say it's an unalterable, blockchain's a immutable log. That's actually a false statement. It's not immutable, it's tamper-evident. If somebody changes it, it's easy to detect. It's easy to change, but it's easy to detect. So it's not immutable. It's immutable kind of conceptually because of the easy detection, but it's a not accurate statement. So you'll hear a genesis block. So what is a genesis block? Somewhere you got to start the thing out. So this thing in this blockchain, I just have a block. I'm saying that the previous hash is 1. I just made up that number out of thin air. It's in index 0. It has no transactions, and its proof is 100. All those numbers are just made up. The only important thing is that it's in position 0 and it has no transactions. So next part is the state. And if you recall those pictures, there was a pool and there was the log, the ledger. And in this case, I have the pool, a transaction pool, and it's made up of transactions. And it has a chain, which is made up of a chain. And the chain is just a list of blocks. And so here in the block, there's a list of transactions. And I've got a to-do there that says, in a real system, a lot of this would be off. It wouldn't be in memory. For this, it's a little educational thing. Having in-memory stores okay, but even in memory, you probably use something like data.sequence because I'm going to use these lists very inefficiently. But the nice thing about them is they print out very well when we start looking at actually running code. So that's why there's list error, but there's also to-dos all over the place. Okay, so now the initial blockchain state is just something where there's an empty pool. There's a chain with one block in it, and that's the genesis block. And there's this proof difficulty 4, and that comes in later. So we'll take a look. So if we start actually looking at this thing running, it says the initial blockchain state should be what I just said. And we can actually run that. Looks like I've been messing around with this. And it should say it passed eventually. There we go. It passed. And I've got a lot of HSpec stuff in here to show what's going on. And I'm actually not going to run it every time because it's kind of you can just trust me that it runs. And at the very end, I'll run the entire test suite. And then if it runs, I wasn't lying. So, okay, so that's it. That's the blockchain. It's got blocks that contain transactions. And it's got proofs and hashes which help make it immutable. And the proof is how you just prove that you're okay to add something to a blockchain, which we'll get into more. And then there's the blockchain state, which has a pool of transactions that are eligible to be put in the blockchain, but they're not there yet. And then the actual chain that you have at any particular time. So the first thing you want to do is add transactions to the pool. So we've got these things coming in, and we want to somehow get them into that pool. And how does that happen? Well, I have add transactions to pool, so I give it that BC state that we just looked at. We give it a single transaction, and it returns an updated state. And the first thing it does is see if the transaction's already in the pool. If it is, you just return the unmodified state. Otherwise, you update the pool to contain that transaction. And once again, like I said, this is a big to-do. I'm appending this at the very end, which is super inefficient, but it's okay for, so it's great about talks. You don't have to worry about performance. And if you look at it, I've got, here's the initial BC state. I add transaction 1, and that returns a new state, which I then give to another call to add transaction to pool and give it transaction 2. So we see now we have 2 transactions in the pool, but the chain hasn't been updated yet. And the adding, if you recall what it said to add transactions to the pool, the only, in this particular blockchain right now, the only properties of a transaction are equality. So I won't let 2 things that are equal go into a pool or into the chain at the same time. Other than that, they're just a byte string that no one's looking at. So if we also want to make sure that that is actually tested. So here I'm doing add transaction to pool, transaction 1 and 2, and then I'm going into that updated pool, which is S, feeding that back in and adding transaction 1 and transaction 3. And this is just to make sure that only that transaction 1 only gets added once. And depending on your blockchain, you'd actually do a lot of checking beforehand, and these bytes would actually mean something, so you'd actually have to do a lot more testing than just equality. And when we actually turn this near the end of the talk into a cryptocurrency, and then we'll see that in action. And searching the chain or pool are just folds. I'm folding over the list, and I'm also giving a fake 0 transaction. This just turns out to be a useful thing. So mining. Okay, mining is the part where we put things into the pool, and the miner has to grab 1 or more of the items in the pool and form a block, and then add that block to the chain, and also let others know about it. Well, and I'm going to break this down into 2 steps. So the mining is just going to add this here, and broadcasting it to the other nodes, that comes a little later. So we're just going to look at how the mining is actually done right now. So mining, what it does is it takes, in this particular blockchain, and this is a little bit like Bitcoin and a little bit like other things. So this is, I'm not saying this is how Bitcoin works. This is how, just the basic concept of blockchain. It's not necessarily Bitcoin. Anyway, you grab the last block, you grab the current proof difficulty number, and if you recall, that was 4, and that is put in the state, and that can be adjusted depending on conditions in the network. You can make it harder for miners or easier for them to start mining things, and you'll see how the proof difficulty works. So I then do a proof of work. This is become eligible to put a block in the blockchain, you need to do proof of work. There's other types of things: proof of stake, proof of elapsed time, BFT, Byzantine fault tolerant, Raft, all sorts of things. This one's using proof of work, and because I'm sure you've heard that one a lot. It basically means proof of using a lot of electricity for no good reason, which is really unfortunate. And this is yet another one. So, and then I take the idea is I create the last block, I find out what the current proof difficulty is, I form a proof that says something, that says I've done that proof. Once you can show that you've done that proof, and then you'd also take a hash of the last block, and then you add a block with that previous hash and the proof that you just made. So adding a block is pretty straightforward. It basically says, I'm taking the length of the blockchain, which is going to be its index, and there's a big to-do there because the length on a list and all that, but if you were in data.sequence, it'd be different. I take all the transactions in the pool in this case. Sometimes other people would maybe take a certain number, and you've probably heard about Bitcoin and a lot of fighting over the size, the number of transactions in a block. Anyway, this one's just always grabbing all of the transactions and the proof. So it just forms a new block. It updates the state such that now it's set the transaction pool to empty because it just took them all and put them in that block. And then it adds that block, newly formed block, to the end of the chain. And that's done. And what it returns in this particular function is the updated state and the block that you just mined. And that's kind of the terminology. You mined one. You minted. You created this new block and added to the chain. That's what the word mine means. So let's take a look at mining. So add block. I've got an initial blockchain state. I'm adding transactions 1 and 2. And after I do that, I do mining. And so what we should see here is that the transaction pool is empty. Even though we had added 2 things to the pool, mining took them out of the pool and they put them in to this new block. And the new block is the second one. The first one is the genesis block that was already there in the initial BC state. And the new block has the index 1, those transactions, the proof, and also the hash of the previous block. And this is important because that means later on, as this chain gets longer and anybody tries to go back and manipulate anything, that's going to screw up the hashing. Because if you hash the previous block, that block's hashed the one before it, and on and on and on. So anywhere in there, if you change any data, it's going to reflect, because the hashes won't line up anymore. And that's the idea of a tamper-evident blockchain. It is not immutable. It is tamper-evident. You can tell when somebody changes it. So the next thing, this is another test, and that's this one's the test that if something's in the chain, they're not added to the pool. So I'm doing a similar thing where I'm doing transactions 1 and 2, then I do mining, and then I try to add transaction 1 and 2 to the pool. But if you actually look at this data here, let me get this. This one looks exactly like that one because it says they're already in the chain. So, and that would happen if, for instance, somebody's mined something and there's been some transactions flying around the network, but they haven't quite arrived at a particular miner yet. And so once it, or a duplicate arrives or whatever, it will detect like, no, I've already seen that one.
So this checks that there's both not that transaction existing in the pool and also not that transaction existing in a mined block.
Correct, yeah. It's either, if it's already in the chain or in the pool, it just drops it.
How far back does it just keep searching the chain all the way back?
Well, this particular one, yes, it does go all the way back. In a real blockchain, you would never do searching of the entire chain because it'd be super duper inefficient. But conceptually, it's kind of the same idea, is you don't put it in if it's already there. And what that means, if it's already there, we'll get into. Because this one's, like I said, this particular, where we're at right now, it's just equality on bit streams. There's actually more if you have a coin or something, what that means, that it's not there. It means it hasn't been spent.
How would an existing huge blockchain verify that it's not already there?
I will show that later. That's coming up. And the hashing is just real simple hashing. I'm just doing SHA-256. And when I hash a block, it's really a poor man's hash. I'm just showing the block, packing it as a byte string, and then hashing it. So if you change the order of any fields, everything goes to hell. So this is not recommended, but it's quick and easy and quick and dirty, right? So now we're getting into the proof of work algorithm, which is probably the most interesting. Because if you've seen now so far, it's just mechanics, right? Put something in the pool, if it's not there, and then take it out of the pool and put it in a block, and then add the block to a list. So there's really not much to that at all. The proof of work is kind of where it gets interesting, and that shows to others that you can put something in. And it also, like in Bitcoin, they've got it timed so it takes about 10 minutes for every block to come in. And it's the idea of proof of work is that expensive and time-consuming to do the work, but it's instantaneous to check that a proof is valid. And this, as we go through this now, you'll see why that is actually the case. So in this proof of work algorithm, I'm looking for some number that when I take the hash of the last blocks and I append it with the last proof, and then I have this new proof, this new number, and I hash that, and I look at the hex digits, that the leading n are zeros. And the n that's what we've seen all along, proof difficulty, and I've set it to 4, but it can be varied on how much you want to check. So let's take a look at how that works. Proof difficulty, I'm given, for proof of work, I give it the current proof difficulty, I give it the last block, and then I just start at 0, and this is literally just a brute force search. And that's the idea with the proof of work. There's no smart strategies like, oh, I'll start at number 3000 and find it, or I'll start, come in and do binary thing where I narrow the space down. It's basically brute force search. So I'm starting from 0 and going on forever till I find one. And I'm also using fold-R, which is not necessarily the right thing to use for a list, but I'm using fold-R here in this toy chain because fold-R has this nice property that, one, it can handle infinite lists. And the reason it can handle that is because when you can bail out early. And you'll see that in a minute. So I get the last the proof from the last block, and that's what this thing was, doing a hash, and I take the last proof. I take the hash of the last block, and then where's the new proof? Oh yeah, the new proof. The new proof is just whatever current number this is, and I check that is that a valid proof. And if it is, then I'm done. So I take the new proof. And that's where I'm saying the fold right, because fold right in this case is not looking at the accumulator, then fold right exits early. So this is the new proof, and otherwise, well, keep trying. So it'll just go on. And I'll actually run this one because you can actually see, actually let's do it right now. So you actually see it hang there for a minute because it's searching. So it is doing what we're supposed to do: use electricity for nothing. So let's see now drop down. So that's the higher level. So now we're going to look. Well, let's test that out. So I'm building a chain. I'm start with the initial state. I'm adding transaction 1, and I'm doing mining. And I have this new state which has a blockchain with transaction 1 in it. So if I look at that, I'm going to find that the proof of work for the Genesis block should be basically what is ever in the proof for that chain. And if I look at it this way, it says that number turns out to be 52,668, which is not very interesting. So let's drop down some more to see what that means. So validating a proof, it takes the proof difficulty, the last hash, the last proof, and the new proof, and it looks builds up the evidence, which was those same 3 things, and based on that evidence, which is really just a guess, it uses the proof difficulty to look at the first proof difficulty elements. And so it's just doing a take, and in this case it's taking the first 4 hex digits of the guess, and then it's replicating the zeros the same amount of time. And so if the guess has that many zeros, it is a valid one. So it's just going to keep guessing. And the evidence is just what we did before. Once again, this is doing shows and packs, not recommended, but okay for this, and then doing hexes. So in this one, we'll actually finally see that the evidence, when I take the Genesis block and I'm going to build a block on top of it, is going to be this particular hex digit, and there they are, 4 zeros. So there's your proof of work, and it's just I find that really sad. And then that other number, that magic number we were looking at before, 5,200,668, that is the next number here. When it's that's the number that when you append its byte stream representation with the previous block and the previous proof, then that's the number that gives you the 4 zeros. So we've covered now getting things off the network, dumping them into the pool, and things, transactions, whatever you want to call them. Right now they're byte strings. And then we take them from the transaction pool into the block that gets put on a blockchain. That's called mining. You can show to others that you mined that by doing proof of work. And now you've got to actually somehow, different nodes in the system have to end up with that exact same chain state, and they're not related to each other. So that's where the next piece comes in, the consensus algorithm. And so I should have had that up this whole time. So whoops. The threads going to the transactions going to the pool, then going to this log, and remember the transactions get shared between each other. And then when you mine something, you tell everybody else about it. And how do they decide who wins? So in this particular consensus algorithm that I've got, it's just the longest chain. And in longest in this toy chain just means literally the length of the blockchain, which doesn't count like how many transactions are in a particular block in that chain. That's another way you could define length. And so there's different ways to define longest chain. This one is just the number of actual blocks. So what I'm going to do is I've given the current state and given a bunch of other chains, return the potentially updated state, and if it's updated, I get returned an updated environment and true, and otherwise I will return false, meaning nothing changed, and if something goes wrong, it'll also give me a failure reason. So doing that is pretty simple. I just do a fold looking for the longest chain. Once I finally get the longest chain, I check that it actually is a different chain, because if it's my same chain, then nothing changed, and I just return the same state that I was given and false, saying nothing changed. But if it is a different chain, I check for validity. I want to make sure that the chain is valid, and we'll see how that's done in a moment. And if it is a valid chain, then I update the chain state so it now points to this new chain. So I've thrown my chain completely away, and I've also updated my pool, and that's kind of interesting in this particular chain, and I do this thing called resolve transactions, and that's actually the hardest part here. And all this means in this chain is that to resolve the transactions, I look at everything in my pool, and I remove the transactions from my pool that are in their chain because they've already been committed. So if they're in my pool, I don't want to double spend them or don't want them to happen again. And if there are transactions in my chain that aren't in their chain, that means they still need to be dealt with, so I got to get them back into the pool. So that moves this stuff around. And that's actually the hardest part of that algorithm. And I'm actually not going to show an example because I won't get to the next part. But anyway, the longest chain, let's take a look at it in action. This one's pretty simple. It just says I've got a chain which has a block, the genesis block, and another block which has this transaction 0. And if I do longest chain against the initial blockchain state, it's going to be the longer one. And it's commutative, so I can switch those around, and you still STX0 comes out. And I'm going to skip all this other stuff because it's 10:30. But there's this can get arbitrarily complex, and let me just show you a couple of diagrams to. Oh yes, let's look at this thing. Determine if a chain is valid. So first of all, if I'm basically I've found a longer chain, but I'm just not going to take it. The first thing I'm going to do is make sure that it's not empty, because if it is, it's no good. Or if it's one, that it actually is the genesis block there. And otherwise, I'm going to look at every block and make sure that the block is valid. And I do that by having counting from 1, because I'm starting at index 1, and that 1 is just so when I do error reporting I can say which index it's at. It's not fundamental. I take the current blockchain and the tail of the chain, and that's just so I can do, you know, when you've seen the definition of Fibonacci in Haskell, where they do that thing where they, is it Fibonacci or yeah, it is Fibonacci, and they offset it by 1. This is the same idea, because I've got to compare two blocks at the same time. So test valid chains. I'm going to skip past this because I really want to get to the coin part. What a valid block just means, this is what a chain is just going through to make sure that every one. But for a block, it says, given a valid block, one that I know, and it starts at the genesis block. And once again, this is educational stuff. You'd never do this in a real blockchain, always going back to the genesis block and winding all the way up to the current. That would be insanity. But conceptually, that's kind of what's going on. But so I'm hashing the valid block and comparing the block that I'm checking and taking its previous hash, and it should hash to the same thing. And if it doesn't, then it's going to complain about the hash being wrong. And then I'm going to check that the proof is valid. So given the check block and given the valid block, I'm going to make sure that when I construct that proof, the number that that new block has in it is indeed a correct proof. And that's where I was saying it's real easy to check a proof, because all you have to do is look for make sure that it has the right amount of zeros. Whereas finding that number was a lot harder. Okay, now to make this thing run, so everything we've looked at so far has been pure code, and it's all been tested in pure code in HSpec, and that's how we all learned it in Michael's class and everybody else's class. There you go, we did it. And now we're actually going to get in stateful code. So for stateful code, I've got to have that BC state we've been looking at. I've got to have a list of other nodes, how am I going to talk to them on the network, and my own address. And then I put all of that into an IO ref. And now let's actually run this thing. So what I'm going to do is create 3 nodes, and initially they'll all have just the genesis block in their chain, and the curly brackets are the transaction pool, and there's no transactions. So we've got to get that running first. So let's do that. And that's correct. And so I started up all 3 servers, and now in a different window, different shell, I'm going to get us into the initial state. And indeed, if you look at it, there's the 1, 2, and 3. They're actually on 3000, 1, 2, 3. Their state is empty pools and just the genesis block inside their blockchain. So that's where we got to begin with, and that's so I've initialized the environment. Next, I'm going to add a transaction to the pool. And this just uses that pure thing, but it wraps it up. So once I've done that, then I actually update the IO ref that contains the blockchain state. So what that looks like is I'm actually doing a lot of transactions. So this node 3 has got transaction 31 in its pool, and it's telling everybody else about it. This one has 21 and 22, and it's telling everybody else about it. And this one has 11, and it's telling. So everybody's received some transactions from clients, and they broadcast them. Besides putting them in the pool, they broadcast them to everybody else. So let's do that.
In doing so, does that prevent those transactions from being added to any other pools?
Say that again?
Does doing that prevent those transactions from being added to any of the other pools? Or could it still be in those pools as well?
Oh, it could already be in their pools. If somehow the client told them two different ones, but they'd already see it in the pool, well, we looked at it earlier, and because it was already there, it would just drop it.
And it would drop it out if it received a message?
It wouldn't drop it out of the pool. It would just drop the second one that came in, the second message saying, I've already seen that, so I'm not.
Hit points where like the messages are out of sync, so they end up both mining it because they both thought they were the only one with the transaction in the pool?
Yes, that can happen, and I'll actually show that. That definitely can happen. And did I run this yet? No. So now I see they've all got those transactions in their pools, and conceptually all those transactions are on the wire at this moment, and they haven't been received. So they've all got it in the pool, but they haven't received them. So if I look what happens after I've received, it basically says I've received, this one's now received all the other ones, likewise, except this particular node, for some reason, has not received transaction 31 yet, so it hasn't come in. Your question I'm going to have to show you during the break, because that actually is kind of involved in, I'm not going to have time, but I actually have diagrams and operation to actually show that in action. So let's now make that work. So now all their transaction pools are empty, and each one of them has a different set. Well, no, 1 and 2 have they have different transactions sets in their pools. Well, actually, this one's the same. It's just in different order, and this one definitely has a different one because it's missing transaction 31. And now, what happens next? So we've added things to the pool, and they've been different depending. And now we're going to actually mine some stuff. And in this case, we're going to say that node 3 is mining all of the things that were previously in its transaction pool, and it puts it into a block. And I'm labeling that block 3B1. That label doesn't exist. It's just so I can show it in the diagram. So then it broadcasts that block to the other nodes to say, here's a candidate. And notice, besides sending that transaction 31 somehow is still flying around the network, and number 2 hasn't received it yet. So to mine that, it's the same thing as we've seen. I do the exact same thing. I just mine, which we'd already showed in pure code, and now I do it inside this atomic modify IO ref. And to make that actually work, now we see that this guy has the new block with all those transactions in it. These still have their old stuff because they haven't received that new chain yet. And that's where we'll see that here, where once they do see it, then they will update their state to be that longest chain. So in other words, they're throwing away their chain and taking in the longer one instead. And that's why you hear things about Bitcoin like it takes 10 minutes and such, because besides the proof of work, it's got enough other agreements on longest chain, because you can be at a longest chain point, but then some later, like, oh no, here comes a longer chain. And so you've got to replace it. And it turns out that after about 10 minutes or so, then you've had enough of those other chains put on that, yeah, okay, it's probably not going to get rolled back. It just gets harder and harder to actually get to a state where you'd ever roll back. So once those are received, let me see, we showed that, right? Oh, yeah, and the last thing is when that transaction that was flying around here finally arrives, it says, oh, there it is, 31 arrived, but I've already got it in my chain, so I'm done. I'm not going to do it. Okay, so I've got 8 minutes to do a coin. Oops, and I... What happened? Interesting. I think I fat-fingered things. Okay, so we've been just, all that is the mechanics of blockchain, but the blockchain was useless because it didn't have any value other, dumping a bunch of byte strings, and not very useful. But now we're going to turn it into our own crypto coin, and afterwards I'm taking money. So if you, I'll have my ICO at 12:30, 12:30, and I'm sure y'all want in because it's. My son bought a house with his Bitcoin profit. He told me, "Dad, buy," and I didn't, and he did, and I lost. So this is a coin, and this coin comes out of the, there's a thing called, that's known as the Princeton Bitcoin book, which I'll have a link to, which is a pretty good book if you want to read a lot of stuff done by a lot of great people like Andrew Miller and such. And he has a coin near the beginning called Goofy Coin. So this is G coin. And what it means is to create a coin, all you have to do is have a create constructor, and it contains a unique ID. And then you sign that value, and then you have the signed transaction, which contains the signature in that. And once you have that, you've got a coin. So this guy is pretty lucky. He can create coins any time he wants. And to transfer a coin, you take, as long as it's rooted in a create coin. So you've got this coin that was created by this G, with its secret key. It signs with its secret key. And to transfer it, you give the public key of who you're transferring it to, and you have a hash of the coin that you're spending, and then the person that's transferring the entity that's transferring the chain signs it and becomes a new signed transaction. So the entity receiving it has its public key here. The entity that owns the coin signs it. And then there's this hash thing linking it up. And right now, that hash thing is just kind of, where does that hash to? Well, you know what hashes this, but where does this live so you can check it? Right now, it doesn't live anywhere. It's just floating around. So what that looks like is I have a transaction with create coin and a UUID. The labels are just for so you can see things easy. They're unnecessary. And a transfer coin is what we said. It's got the hash of the coin being spent and the public key of the entity that's receiving it. And a signed transaction is just one of those things above, and the signature of that thing under the private key of the entity transferring the coin. So to create one, you just make sure that you have a secret key of the entity creating it. It creates a UUID and then says create coin, which all it does is creates a coin, literally, data structure, and signs it. That's it.
So
and
byte strings, you're now putting these on.
Yes, but I am turning them into byte strings, and which is not necessarily an efficient way to do it, but it makes the example blockchain pluggable because they're always just byte strings, and so when I plug this later into the thing, I can just decode them and say, oh, it's now this. But you're right, this is now what those byte strings are going to represent these coins. So we're not going to run through this, but creating coin is, you have the UUID, you generate some secret keys or have one in your back pocket or somehow, and you grab the secret key. And to verify creating coin, this just shows that if you have a created coin and you have the public key of the creator of that coin, it's going to verify. And if you have somebody else's public key, it is going to fail. So now let's go to, wow. Okay, transfer coins, very similar. I'm going to skip all of that. And later, now, when you get a new coin coming into the system, you've got to determine if it's valid. And there's two things that determine. One, when you start following all those transfer links, sooner or later it's got to, one, they have to be signed correctly. And sooner or later it's got to be rooted in a create coin and that create had to be created by the public key that you know of that in this particular system there's only one person that create coins, so it's the public key of Goofy. And that's what this is. And the other thing is you have to make sure it's not double spent, which this doesn't do yet. So valid coin, what it says, is if it's a created coin, just verify the signature. That's where it ends. But if it's a transfer coin, then I've got to look up the hash, and somewhere I look it up. Right now, I'm just using a hash table. But in a blockchain, conceptually, you'd be looking it up in the blockchain. You'd actually well, I'll show the optimization of that. So you look it up and see what it's pointing to is either a create coin. If it is, you're just going to recurse and you're going to end up right back here verifying the create coin. And if it's another transfer, first you're going to verify the signature on that transfer is correct. And if it's not, then you're error out. Otherwise, you go back around again and check that transfer coin is valid and going to end up sooner or later in create coin. So this is kind of what would happen is you'd have a whole bunch of these, and in this case, this coin would be a valid, quote, unspent coin because it chains through all of these. These have been spent. This one's unspent. Well, this is unspent, but it's also double spent because this is saying A gave it to J and it gave it to B1. So that's kind of the idea of double spending. I'm going to go... Let's go back to the other one now. So, where is my double spent? All right, this is the idea of double spending, is that you have this created coin, and let's say it was transferred correctly once to A, so G transferred it to A, but now A is transferring it to both B and to J. And so what you have to do is you have to determine that this signed transaction, the hash here doesn't already appear somewhere else. So when they do this once, great. But if something else comes in later and it has a hash of something that's already in the network, then you shouldn't let that go. And that's where, in this particular blockchain, this basically what the blockchain's for, is to prevent double spending. So it's a place that's tamper-evident, and you record all of these transfers, and you can't transfer the same thing twice. And all this does is say, given the creator, whoever eventually created these coins, and a transaction to verify, I'm going to search the chain for that hash. And remember, this particular chain is just a bunch of byte strings. And if you find it, then you decode it and say, great, I found, and you, where is it? Where is it? Where is it? Is valid coin. Where is it where it says, what I'm looking for is where it's actually asking the question. Yeah, I think I've got a bug here because this is just saying that I'm looking, oh, that's the lookup. No wonder I got confused. This is calling is valid coin, which is on the previous page, and it's using this lookup function. So it's doing the same thing where it's just making sure it's rooted in a create coin. And I think, well, we're at the end of the hour. But basically, when you're asked if it's a valid transaction in this very, very inefficient blockchain, is you look and you see that is it a signed transaction. If it's already in the pool or already in chain, then it's not a valid one. Otherwise, it's okay. If it's a transfer, it's the same idea. Is it already in there? Then if it is, you're done. And I think, oh yeah, this last piece, UTXO, if you're in the last thing, all this stuff about searching the chain and all the way up and down is super inefficient. And this is kind of the idea of UTXO. It just means unspent transactions. Instead of all that searching, you just make sure before you put something in the blockchain, make sure that it's valid, meaning it's rooted in a create coin, and also that it hasn't already been spent. And the way you determine it hasn't been spent is you create this cache, which is a UTXO cache, which is the unspent transactions. And that looks like this. The only thing that's going to be in that cache are these two things, because these have already been, all of these have been spent. So this was a create coin and then a bunch of transfers. This is a create coin, but you notice it's not rooted. This is a transfer coin, but it's not rooted in a create coin, which we'll get to. So the unspent transaction would only have that particular thing in it because it's the only valid one and it is unspent. So that's the idea of UTXO. And in this case, I'm pretending like I've got a new node that's coming into the blockchain network. And to do that, it somehow has got to get up to date with where it's at. And in this case, the way it's getting up to date, it's given the entire blockchain, and then it replays everything in it, in a sense, to get this cache going. And the cache just says, give me all the transactions in all the chains, in the chain, in all the blocks, give me the transactions, flatten those out into one big gigantic list, decode, map, and that's because they were bit strings, and now I want to turn them into signed transaction. Then I'm going to fold all over that and create, and with map insert, and saying that if it's a signed create coin, just stick it in the map. And if it's a transfer, then take it out of the map. And when I'm done, if you look at the test on this, if I do the create coin and I give C to A, and then I give that A to B1, and then I give B back to A, and then I give A back to B2, that's basically what that picture was a moment ago, which was this one. It's basically, it's trying to get to this state where we end up with that B2. And we look at it in the test, and after all those tests, we should see that, yeah, A to B2 is the only thing that's in that map. So now I don't have to go searching the chain every time, and that's the idea of doing a UTXO. And I think I'm out of time, so let me just put up one other thing. And one thing I wanted to do, but there's just not enough time. That's kind of the idea of using the blockchain, and the state of the blockchain is actually the data. But you could also have off-chain data and smart contracts. And by smart contracts, that means they can do anything that the contract language will allow them to do. And kind of the simplest smart contract is a key value store. So you say, here's a key, put its value. But you actually don't put the value in the blockchain. You're just a database or in-memory key store that just has that key. But everybody then, it keeps all those key values in sync across all the nodes. And that idea of putting and getting is then just a smart contract. And what that looks like is, that initial picture I showed here is you have some command, transaction, whatever you want to call it, and instead of just dumping it as a byte string into here, you actually interpret the command. And that's the smart contract, is interpreting the command and deciding what to do with it. And we did a little bit of that with the UTXO, and we did a little bit of that when we were checking the validity of the chain. So, but somebody wasn't writing a contract. That was kind of burnt into the system. But if you actually allow people to plug in their own contracts, then you're going to have some sort of execution engine here that will run that and maybe have state that it keeps off to the side. And what gets put in the ledger is the fact that you all agree on the state. And that agreement on state is usually done by way of, you've probably heard of Merkle roots, which we can talk about in the hallway. And that's stuff like that gets put on the blockchain. But the actual state of the contract quite often will be off-chain. And that's it. That's pretty whirlwind.